A patient with Alzheimer's disease will experience accelerating cognitive decline over a 20-year period. But if you look at the total volume of amyloid plaques in their brain across that same clinical course, the burden is essentially stationary. Faced with this, the standard practice in quantitative neuropathology has been to track the disease by counting the deposits, treating the plaques as a simple tally. This chart shows total plaque count against cognitive function over a 20-year timeline. The count remains flat while the patient's functional collapses. Tracking a stationary variable to explain a progressive decline guarantees a statistical failure. The tally does not map the injury. In 1910, a psychiatrist named Fischer published a 100-page monograph based on 275 brains. Fischer evaluated the exact same lesions we study today, but he refused to tally them. He chose instead to measure the specific morphological state of each individual deposit. He lacked immunohistochemistry, fluorescent tags, or any modern molecular tools. He relied entirely on a silver impregnation stain and strict deductive logic. He categorized the life cycle of the lesion into an 8-stage classification table, mapping how a single plaque develops and interacts with the tissue around it. The 20th century discarded Fischer's staging scheme in favor of a generic count. By treating all plaques as identical units, the field threw away the exact morphological variables required to predict neural injury, blinding researchers to the mechanics of the disease for 100 years. Look at these early fibrillar deposits from Fischer's plates. Stage 1 is the 2-micrometer star. Stage 2, the morning star, introduces radial, straight fibrils. A distinct space then opens around the deposit. Fischer called this the halo, noting the surrounding neuropil explicitly vacates it. This observation led to a precise mechanical rule. In these early stages, the growing mass displaces the nervous tissue. It does not destroy it. You can see the axis cylinders of the neurons physically bending in arcs to accommodate the expanding inclusion, proving the relationship is mechanical. By stage 4, the deposit becomes a wheel, featuring a central star, radial spokes, and a closed peripheral ring. Tracking the distinct tint of his stain, Fischer proved this outer ring was not host tissue, but chemically foreign to the nervous system. The early senile plaque is a highly organized, expanding foreign mass. It pushes healthy tissue outward, establishing a structurally defined perimeter where the actual battle between the deposit and the brain will take place. Fischer lacked modern chronological tracking, so he built an internal clock out of his stain. He noticed that young silver-impregnated threads stain black, while older threads take on a brownish tint. When he applied this rule to a single mature plaque, the center of the deposit appeared brown, and the marginal rim appeared black. If the outer rim is the youngest color, the plaque must grow by accreting outward, continuously adding new material to its periphery. 110 years later, high-resolution confocal and 2-photon imaging investigated this exact core and corona geometry. The structures Fischer identified in silver map perfectly onto modern fluorescent channels, matching the compact center shown by thioflavin S and the displaced perineuronal matrix shown by aggrecan markers. Modern imaging reveals the critical element Fischer's stain could not show: plaque-associated microglia, forming a dense physical barrier around the deposit. These immune cells actively compact the amyloid. They prevent its outward expansion and shield the surrounding neuropil from highly toxic protein hotspots. Fischer deduced the exact architectural consequences of microglial compaction. Using a single stain and rigorous logic, he mapped the containment barrier, predicting the neuroimmune dynamics a full century before the cells could be visualized. So at what point does this expanding structure begin to harm the surrounding brain tissue? Fischer answered this by tracking club-shaped axonal swellings, what we now call dystrophic neurites. He used these massive spindle-shaped distortions as a direct indicator of tissue damage. This chart plots the occurrence of these damaged axons against the morphological stage of the plaque. The data forms a sharp inverted U-curve. The clubs are absent around the youngest deposits in stages 1 and 2. They peak sharply around the mature containment barriers of stages 4 and 5, and then they disappear completely at stage 8. Modern neurobiology confirms why this happens. Toxicity is driven by a gradient of diffusible species at the plaque's edge. This toxic material escapes into the halo space to damage neurons, only when microglial compaction is incomplete or struggling to contain the mass. A stage 2 plaque is relatively inert, while a stage 5 plaque is highly toxic. Tracking total plaque count tells you almost nothing, because injury is dictated entirely by the precise morphological state of each containment barrier. For decades, the English-language secondary literature universally misread Fischer's final category. They assumed stage 8 represented end-stage disease. The morphology of stage 8 looks devastating. It is a massive, diffuse infiltration, where the thread masses are borderless, and the axis cylinders and fibrillar networks are completely wiped out. But Fischer explicitly stated the opposite in his German text. He defined stage 8 as a younger process advancing rapidly through tissue that lacked the resistance to contain it. This explains why there are no axonal clubs in stage 8. The rapid, uncontained infiltration destroys the axis cylinders entirely, leaving no axons behind to swell. Stage 8 is a catastrophic failure mode of the brain's containment mechanics. It proves pathology severity is dictated by the resistance of the host tissue, not by the amount of time the disease has been running. This morphological staging dictates modern clinical genetics. Take the human TREM2 R47H mutation, which significantly increases the risk of Alzheimer's disease. In patients with this variant, the total plaque count remains completely unchanged. Instead, their microglia suffer a reduced ability to physically envelop the deposits. In Fischer's vocabulary, the mutation traps the brain in stages 3 and 4. The plaques remain uncompacted and filamentous, exposing the surrounding neurites to valent toxicity. The genotype alters the morphology of the lesion, leaving the tally alone. Any therapeutic strategy based on counting plaques will miss the biological reality of the disease entirely. The final historical irony lies in Fischer's own notes. In 1910, he wrote a hypothesis for the chemical origins of the senile plaque, proposing they were, quote, precipitated from a dissolved form, far from their site of origin, assembling crystal-like. He perfectly articulated the modern amyloid hypothesis, soluble proteins precipitating far from their site of origin into dense fibrillar assemblies. Yet he ultimately rejected his own correct hypothesis. The structural orderliness of his stages seemed too deliberate for a simple precipitate, and he lacked the concept of nucleated seeded polymerization to explain how chemical precipitation could build such precise architecture. Oskar Fischer had the spatial dynamics, the mechanisms, and the correct predictive variable over a century ago. If we want to solve this disease, we have to stop counting the ruins and start measuring how the battle is fought at the perimeter of every single plaque.